Hi, this is Brother Tony. Hope you had a good weekend. Hope you had a good open notebook quiz. And we're going for the next week. So this week, we're taking a look at mathematical models. And we're going to spend a number of days on them because really this is why we study math, is we want to make predictions about the real world. And so a mathematical model is an equation that allows us to make predictions about our world. In this section, we're just going to be studying linear functions, so straight line models. Now, since this is real world, domain and range is important. If we're doing something based on time, we do not recognize negative time. In our real world, there's no such thing as negative time. So, in this short tutorial, we're going to look at how do we derive these functions. Okay, so let's begin. So here we are. This is a totally made up graph, but I'm saying somebody did an experiment, and they did it a number of times like a good experiment would be, and they took a look at the number of gadflies that they captured versus time in days. So every day, starting with day 3, must have been a long weekend, they didn't count day 0, 1, 2. Starting on day 3, they took a look at how many gadflies had survived, and they went all the way to day 16, right there. So from day 3 to day 16. So that is our data. And you should recognize that from your biology labs, from any of your chemistry labs. It's not always on a straight line, but it does seem to make a linear type formula. So how do we get that from all these data points into something we can use as a linear function in a mathematical model? Well, I'm glad you asked. Now, there is actually a mathematical formula to find the line of best fit. And it's basically a least squares type formula. But for what we will do, what will be good enough for us right now is we will draw a line, and you see I've drawn a line that basically has half of the points above the line and roughly half of the points below the line. And we will extend that to both the x-axis and the y-axis. The next thing we do, to begin making our mathematical model, we have to take 2 points on that line, and we're going to find the slope. Now, a couple things about using the 2 points. First of all, you see I have graphed the data on engineering paper, and you see the 2 points that I have selected actually intersect at whole numbers, both on the x and the y planes, at 7, 19, 10, 14. What that allows us to do is allows us, using those 2 points, to get the most accurate measurement possible. Now, just to remember, those 2 points are not necessarily original data points. These 2 points, I looked at our straight line and found those 2 points, those coordinates, those ordered pairs that would be whole numbers. That will give us the best straight line mathematical model from this data point. If you don't understand that, please go back, listen to this again, and or in your notes, write that down saying you don't understand and ask me in class. So now that we have 2 points, let's solve this, let's create a mathematical model. Okay, as I was working through this problem, I noted that the second point was not 10, 14, it was actually 11, 14. If you don't believe me, hang in there for a minute and we'll go to the original graph and I'll show you that that point is. But take my word for it, or at least take my word for it for a minute. Let's go figure out how to do the equation of line. Well, you have 2 points now. Slope is y2 minus y1 over x2 minus x1. y1, x2, y2. M equals y2 minus y1 over x2 minus x1. That equals negative 5 over 4. But we have to find the linear equation, y equals mx plus b. So what should we do? Let's take this second point and use that. So 14 equals m negative 5 over 4 times x, which is 11, plus b. 14 equals negative 55 over 4 plus b. I did a little math before. Negative 55 over 4 is negative 13.75. We add 13.75 to both sides. That gives us 27.75. That equals b. Our equation now is y equals 27.75x. Let's back that up a bit. Y equals negative 5/4 x plus 27.75. But we're no longer using x and y, are we? What is our independent variable? Our independent variable is time. Our dependent variable is number of gadflies. So how we should write this is g equals negative 5/4 t plus 27.75. So what are we saying? We're saying that every day, on average, 1 1/4 gadflies die. Poor gadfly. Okay, let's go to the next one. So here's our equation. G equals negative 5/4 t plus 27.75. Now, does that make sense? We look over here. At day 0, our intercept is roughly 27.75. And then as the days progress, at about day 15, we see there about 10 gadflies. Day 16, and there is no longer any data. However, we would say that at about day 23, that there would be no gadflies left. And that's by our linear model. Now, at day 24, we would start getting negative gadflies. 25 negative gadflies. But in real life, there's no such thing as a negative gadfly. So if we want to ask what our domain is the values of x, the reasonable values of the independent variable, in this case time, we would go from 0 to 23 days. And then the range, the number of gadflies, we could make a predictor that at 0 days you could have roughly 27.75 gadflies. Perhaps you started with 28 gadflies. And then by day 23 you're down to 0. So the range would be 0 to 28. So now we have an equation that can make predictions. So if you said at day 15, how many gadflies would there be? Well, we could look at the chart. We could say, okay, here it is, day 15. It looks like we should expect to see about 9 gadflies. But we could also do this mathematically. So we could say G equals negative 5 over 4 times 15 plus 27.75. And what does that get us? And that gets us 9. So the ordered pair would be 15, 9. Okay, that's it for the first one for mathematical models. Take good notes, come to class with questions, and we'll work on these in class. Have a good day.